All right, so experiment 3 involves spectroscopy. Today, you know what we're doing? Spectroscopy. And do you know what spectroscopists do? They look at how light and matter interact. That's what spectroscopists do. And there's different types of spectroscopy and different types of spectroscopists. And so we have gamma ray spectroscopy. You know what gamma ray spectroscopists do? They look at how gamma rays interact with matter. Or what about X-rays? X-ray spectroscopists? Same thing. What we did was UV vis spectroscopy last time, and that's what we're doing today, except we're only doing near UV because that's all our spectrometers can measure. And they can measure a little bit of near IR too. The window's a little bit wider. And so our window's 380, so we only get 10 nanometers into UV, which is not much. And it goes to 899 or around 900 nanometers, which is a little bit into the 900 nanometers would be a little bit into the IR. And so we do a little bit of UV vis IR. And then we have IR spectroscopists, microwave spectroscopists, radio wave spectroscopists. How to set it up? Well, okay, you take the USB cable, plug it into the USB port on the LabQuest 2, which is a regular size, and then there's the smaller USB thing on the, what do they call that thing? The SpectroVis. SpectroVis because it's primarily visible spectroscopy. And then you're done. You might have to plug in the AC cable, but that's it. You have 2 USBs, you don't need to use them both. You have an extra. So just leave one in the box. All right, but before we do anything with this, we need to talk about spectroscopy a little bit more. There are 2 types of spectroscopy. There's what we call emission and absorption. In experiment 3, we did emission spectroscopy and we generated emission spectra. Spectra is plural, spectrum is singular. And so let's look at the emission spectra, or spectrum. The thing about emission is you're measuring what light is emitted from matter. And so we collected the emission spectrum of hydrogen. What colors of light come off hydrogen? Helium, etc. And so we have different ones. If you look at the emission spectrum of the sun, the solar spectrum, what colors of light did you see come off the solar spectrum? And so what did it look like? And so we had the backwards. We had Roy, G, Biv, backwards because we started at violet. But what did it look like, the solar spectrum? All colors of light were emitted. And so what does that look like in the emission spectrum? Do you guys have a pretty good memory? What did it look like? Okay, in other words, was there much UV emitted? Do you guys recall seeing much UV? at least near UV? Maybe with the sun, but how about with this light bulb? Did you see a lot of UV coming off there? No. That's good, right? You don't want a whole bunch of UV coming off your light bulb because UV can cause bond breakage and damage. How about violet? Yes. Red, orange, yellow, green, blue, indigo, violet, yes. How much infrared? Actually, quite a bit of infrared because you saw it go down into the colorless region out here. Remember that? And so this is what the emission spectrum of the solar spectrum or the infrared. Infrared will be a little different for the light bulb, but basically what we're looking at is I. Do you know what I stands for? Intensity. And so, fortunately, there wasn't much intensity in the UV. Otherwise, actually, going outside there is more. But we had high intensity of all the colors of the rainbow. And so what we call this is, we call this a band, an emission band. In other words, a band of colors, a continuous band of colors is emitted. Did you see any gaps in the band? No. And so, how about the light bulb? Was it pretty much a band of colors? The white light bulb, this one. Incandescent light. Was it pretty much a band of colors? Yeah. And so this is called a continuous spectrum. Sometimes the bands are very wide, sometimes the bands are narrow, and we call them peaks. Sometimes the bands are extremely narrow. And so when we look at the hydrogen spectrum, we'll say the hydrogen lamp. The hydrogen lamp I'll just call H lamp. And when I look at the H lamp, it turns out we don't get a continuous band. We get this red, we get a green, we get a blue, and you might not have seen this, but there was a very low intensity violet. The most intense for sure was the red. And so this is called a line spectrum. And again, we have intensity on the right, and so this is an emission spectrum. And so the most intense color that we saw was this red color. But it wasn't all the red colors. There was a whole band of red colors, right? It was just one specific red color out of that band that showed up. And so, in other words, hydrogen only emits red, this green, this blue, and this violet. But everything else is forbidden. Let's say a little deeper red is forbidden, a little lighter red is forbidden, orange is forbidden, yellow is forbidden. And so what this is telling you is that the electrons can have these energies, but nothing else. This is what we call quantized. Quantized because there are allowed and forbidden. It might have looked more like a peak, with some width, a narrow band, but it's supposed to be a narrow line like this. Whereas this is what we call continuous. And so this is quantized here in the proper sense. Quantized or discontinuous. So that's an emission spectra. Today, you know what we're going to do? We're going to do the opposite of emission. Do you know what the opposite of emission is? The opposite of emission is called absorption. So we're going to measure absorption spectra or absorption spectrum, different things. absorption spectra are going to look like this. Rather than plotting intensity on the y-axis, we're plotting something called absorbance on the y-axis, the absorbance. And so here the absorbance will increase. So a black body, you know, what colors of light does a black body absorb? All of them. And so does it absorb violet?
Yep.
Yes. And so it absorbs, so we'll get what we call an absorption, you know what we call this? An absorption band. This is an absorption band. And so if we shine all the colors of the rainbow on this, it's going to absorb all the colors of the rainbow, and we'll get a continuous band. And that means if something absorbs all colors of the rainbow, are there any forbidden energies? Or no, they're all allowed. Sometimes these absorption bands are very narrow, though. Anything within the absorption band is like that. The other thing would be like this. Sometimes, if you look at the solar spectrum, and you look at the absorption here, sometimes there are lines. You know, there's a violet that's missing. Say violet. There's a blue that's missing. And then there's a green that's missing. And then there's a red that's missing. And so if you look at the absorption spectrum of the solar spectrum, or the emission spectrum, you're going to see that there's going to be some stuff that's missing. Actually, shoot, this is wrong. Sorry. Anyway, there are different ways of thinking about this. One way is, okay, if I shine light on it, what does it absorb? Well, if it's a black body, it's going to absorb all colors. Well, the sun is like a black body; it should absorb all the colors. And so, but this is not exactly the way I wanted to show it. So let me cross this out. Sorry about that. And let's look at some other things. What would the absorption spectrum for hydrogen look like? And so let's take a look at the hydrogen atom, or hydrogen. The absorption spectrum for hydrogen would look like this. If we plot absorbance here on the y-axis, then it's going to absorb violet. It's going to have a weak absorption of violet. It's going to absorb some blue. It's going to absorb some green, and it's going to absorb some red. But will hydrogen atoms absorb anything in between? No, because those are all forbidden. And so the electron in the hydrogen atom over there can get excited by violet. It absorbs that. It can get excited by these, and only those colors of light. All right.
It's going to be the end of the semester.
Okay, for atomic versus molecular, we typically look at two things. Line spectra occur for atoms, but molecular, we typically see absorption bands or emission bands. Oftentimes we don't do this for molecules because if you subject your molecules to a lightning bolt of electricity, what typically happens is the molecule decomposes and gets fried. And so for molecules, what we do is we just shine light on them and then see what happens. And so that's what we're going to do today. And what we're going to see is that molecules also have forbidden energies and allowed energies based on what we have. So let's take a look at the absorption spectrum. And for a molecular absorption spectrum, what we'll see is a peak here. This peak here corresponds to these energies of light are absorbed by the molecule, which means these energies of light are allowed. Whereas these energies of light over here on the flat part are forbidden. And so we can look at the spectrum of a molecule and see. Now, it's not a sharp line because molecules are vibrating, they're rotating, they're translating. And so that changes the energies. For example, if you're looking at the energy of an electron and the molecule is vibrating, then when it extends out, it's going to have a little different energy than when it compresses back in. And so what we see is these aren't sharp lines, but we get a band of energies that's allowed. Band of energies is allowed. Band of energies are forbidden here. A large band of energies. And so this is what a typical absorption spectrum looks like. Now, let's take a look at the origin of color and the color wheel. We know that are all molecules black? No, not all molecules are black, which means that not all molecules absorb all colors of the rainbow. And so there are many molecules that are colored. And so one molecule is red food color. So let's take a look at red food color.
Before you get deeper into that, you have to
Set up the machine?
the instructions that differ from the different machine versus the spectrometer 20D plus.
The spectrum. Ignore the instructions in the manual.
That's what I'm doing, but then how do you set up the machine?
How do you set up the machine? You set up the machine just by plugging in the cable into the USB port here.
Well, I've done all that, but how do you set up the spectrum?
That we'll talk about when we start collecting data. We're going to collect data in a minute. You're going to see that the data collection for this.
Like 100 milliseconds?
We'll do that together. How about that? That'll be easier. Anyway. So red food color. Red food color, why is red food color red? Is it red because it absorbs red?
It absorbs every other color and reflects it.
Okay, that's one way. So one, it absorbs every color except red, right? It absorbs every color, but red. All right, I'll go with that. It absorbs every color but red. And so all the other colors are filtered out. And so what would the spectrum look like? If it absorbed every other color except red, then what does Roy G. Biv look like?
Spike it red.
Not a spike at red.
Every color.
Yeah, you'd have a big absorption band except for red. And so it absorbs all these colors but transmits red.
Does that mean red is forbidden?
Yeah, that means, in other words, red is forbidden, so the red light's not absorbed. If the red light's not absorbed by the electron, the red light just passes through the matter. Right? I don't know what that was.
What does that mean?
I don't know, I hope it's nothing significant.
That was me.
That was yours? Okay.
That's nothing significant.
So that's what the spectrum looks like, but is there another way that it could be red?
Yes.
And this goes back to the LEDs. They could make all colors of the rainbow by mixing 3 colors. Yeah, red, blue, green, or RGB, red, green, blue. So you have RGB monitors, right? Red, green, blue. You can make pretty much all the colors of the rainbow. So we look at that. There are other ways to make red. We could mix RG, blue in the right proportions, right?
Professor, isn't it red, yellow, blue?
Red, yellow, blue.
Because I remember in kindergarten, the teacher. All the time, because of the color.
No, I'm just giving you an example. I don't know. I really don't know how the red is made in red food color. That's what we're going to find out. You know, it would be nice to be able to predict this, right?
Yeah, it's red, yellow.
No, I'm talking about, you know, I'm talking about the LEDs. LEDs would be, have you ever heard of an RGB monitor? RGB mixes red, green, and blue to make colors. And so I'm just using the RGB as an example. So we take a certain amount of red, a certain amount of green, and a certain amount of blue. You could do this in a photo editing program too if you have something like Photoshop or whatever. You could do the same thing. And you know, so mixing these in different proportions will give you different colors. So the spectrum might have a mix of red, green, blue. I'm not saying it does, but this is just one way it could, right? What did you say? What was yours? Tell me what you learned in kindergarten.
He said yellow.
Okay, yellow, blue, and red. Red, yellow, blue. All right.
To make what?
Those are the prime colors.
Okay, yeah, okay, mix these together to make
Any
whatever.
To make any other color?
Not to make any other color.
Yeah, the other.
Any other? Okay, this is the prime color?
Yeah.
Okay, that's fine.
It's on the hazardous materials classification side.
Wait, how do you make white?
You just mix them in even proportions, red, green, blue.
And you mix white?
Well, I don't know, red, yellow, blue, whatever. Red, yellow, blue, fine. I'm saying it doesn't have to be, you know, it doesn't have to be this, etc. You know, we don't know. You just mix certain colors. It could be two colors that are mixed to make red. It could be one color, who knows, like this. Or it could be two different shades of red that are mixed to make that distinct shade of red. We don't know. We're going to find out though, right? Is there another way? Rather than mixing colors, is there another way? Actually, is there another way to make it? Rather, well, yeah, we can mix colors by, there is another way of making it, and it's like mixing colors, but the way we do it is we absorb the complementary color by looking at the artist's color wheel. This is something you might do in elementary school. And so we do the artist's color wheel, which would be red, orange, yellow, green, blue, and the indigo violet is just one we treat that as, because it's fairly narrow. And so one way we could make red is if we knock out which color. If we want to make red, we knock out the complementary color, which would be green. We knock out green, and then all the other colors will make red when you combine them, average them out. And so this makes red. And so what would the spectrum of this look like? The spectrum of this would be a band at
But except green.
Roy G. Bid. A band at about what? a band, yeah, a band around green. And so if we absorb around green, then the other color should add up to red. And so where's green approximately?
Wait, why is it on top?
Where's green approximately in terms of wavelength? Well, if we compress indigo violet, it's more like, this is 400 to 800, so it's more like 500 to 600 maybe? 500 to 600 if we're compressing indigo violet, right? 500 to 600 what? Nanometers. And so if this were the case, then we're looking for a peak around 500 to 600 nanometers. Does that make sense? You know, this is 400 to 800, but this is compressed, so it's left of center 600. So, which scenario is it? We could try to use quantum theory to predict it, you know, figuring out quantum theory is supposed to be a fundamental description of matter, of the electrons in the atom. And so we aren't going to use, we're just going to experimentally see what it is. You know, maybe it is, maybe, who knows, you know, maybe it's red, yellow, blue mixed in some proportions to make a nice shade of red. That's fine. But today we're going to figure it out using absorption spectrometer, a visible absorption spectrometer, like this. Okay, when we use a visible absorption spectrometer, let's go ahead and set this up. Maybe I'm not going to record this here. This is just the experimental setup. So I'm going to stop the recording here. Unless, should I keep recording this or? No.